Okay, thank you. Uh, Welcome everyone. And thank you, Matthew, for inviting me. And hope all of you will have a informative and interesting session. So, so Matthew has given me this topic of signaling for smart grids. But I guess in many with many of you, you probably the word signaling itself is probably new to you. So what I plan to do initially is take the about 20% or 15% of the time to actually introduce what exactly do I mean by signaling. For and then we will once that context is clear, you will be able to appreciate how exactly uh, what kind of problems that will occur that come up. How do we address those problems? And then I'll show you one example of one particular example by which of my own work, in which I'll show you how exactly we use it. Okay, so since this is in the context of electricity grid, so let's do a little bit of a recap. Here's the traditional view of electricity grids. Traditional view is that the demand for electricity is a combination of cyclical and long-term contracts. This is true even today, more or less. Uh, that the demand that you see in the electricity grid has a fairly well forecastable pattern. It comprises of contracts, some amount of consumption that has been factored in through long-term contracts, and some amount of consumption uh, which is not in the contracts but has a cyclical pattern that's very easy to forecast. The cyclical patterns repeat on at various time scales. They repeat on a daily basis. There's a weekday to weekend type of pattern. Then there is a seasonal pattern across the year and so on. So all of these patterns are fairly well understood and therefore very well forecasted. So the traditional view therefore has been that people have created supply schedules are prepared in advance to track the demand, because you know the pattern. And therefore, you can say the sort of the traditional approach is that supply follows demand. So the fundamental assumption in all of this is that the industry has always been thought of as having an obligation to meet the demand. The industry or the supply side has an obligation to meet the demand. But this is unique with electricity as opposed to many of the other industries. So, for example, if you go to the market today and you don't find say onions in the market, you don't there is no you don't complain to anybody. You just say, okay, there are no onions in the market, that is fine, so let me eat something else. But unfortunately with electricity, when electricity is not there, it there is or electricity is cut, there is obviously a hue and cry about it. This is the nature of the good. The electricity industry has somehow come to be thought of as something as an essential thing, and therefore the industry all has an obligation to meet the demand in whatever way it can. So in order to do this, there is another assumption that the industry has what you can say is supply side flexibility. If the demand is going to be eventually variable, will have variability, but well, even though it's forecastable, there is some flexibility available with the industry to take care of any deviations from the forecast. So, so the traditional view has always also been that the industry is armed with enough flexibility at its end. And now, usually, this kind of flexibility is achieved by fast ramping generators. The big coal power plants and nuclear power plants, etc., take a lot of time to come online from the day the schedule is actually made. Or to change their generation levels requires a lot of time. So any high frequency short term flexibility that is needed is usually provided by fast ramping generators that use diesel or natural gas or something like that. Okay, so this is how we have traditionally viewed the whole electricity industry, and hence as a consequence the electricity grids also. The modern view has, however, is different from this, because countries worldwide have committed very aggressive targets for using renewable generation in their generation mix. And this is because of climate change, because of the shortage, or you can say not shortage, but rather the finiteness of fossil fuels, the and the unpredictability of the of electricity price, of oil prices, of coal prices, and so on. All of these things put together have the impact is that the countries worldwide have ambitious and aggressive targets for using renewable energy in place of fossil fuels. So the advantage that of fossil fuels has always been that you have mined them already, you store them, and you can burn them whenever necessary to generate power as and when required. So therefore they always gave you supply side, the possibility to create schedules as you like, and have supply side flexibility. On the other hand, renewable generation relies mainly on natural forces, so solar and wind generation, and hence is naturally inflexible. It is there when it is there, and when it's not there, there is not much you can do. You cannot make the sun appear from behind the clouds. You cannot make the wind blow on its own. It is it's the way it is there when the natural forces are permit you to use. Okay. There are so that therefore there is now the supply, since supply side flexibility has gone down, the requirement now is to say, well, let us compensate for this by demand side flexibility. So the modern requirement is to have demand side flexibility. Demand level can be so the hope is that demand level can be altered to compensate for limited supply side flexibility through this. How exactly this is to be done is a different matter, but But this is currently the view, and I'll come to how exactly these things are to be achieved. There is also a different angle to the supply side inflexibility that is coming up. Rather than inflexibility, I would say there's supply side unpredictability which is coming up, which is because of supply becoming decentralized over time. So earlier, supply was in the hands of industry alone, and because industry was the one that was generating the electricity, and the consumers were from various different segments of the society. The industry, in the new kind of democratization has happened with the supply, because people are installing rooftop solar, people are installing captive power plants, and then there is open access, which basically allows them to directly use the grid infrastructure to inject any generation that they produce. So this kind of free for all has created a problem where supply also is now is not not only is it unpredictable, it is also uncontrollable, in the sense that you do not know how much people will actually inject into the grid. And so earlier, when it was in the hands of the industry could at least, if necessary, shut down something, or if necessary increase something. Now this kind of decentralization and democratization creates a new problem on the supply side. This further, there is a now need for supply side flexibility of a new kind, where which is not merely by adjusting a few by making a few adjustments by some industries, but rather by making these decentralized sources flexible. All of this means basically you need flexibility on both the demand side and the supply side. Okay, so that we can meet all these new requirements that are coming up. So the only way you can get flexibility is eventually through communication. Okay, so the I forgot to mention there is a third element also, which is now started to come up, which is along with supply and demand. There is storage. So storage is essentially batteries, so they can serve as both supply when needed and demand when needed. So that's another. So they tend to give you some amount of you can say slack uh, in your supply demand equation. So now, if you so suppose you want that you want the demand to change its level, how will the demand know that it needs to change its level? So this for this to happen, you need to actually tell something to the demand, and so consequently, this any supply demand side flexibility cannot happen without communication. So communication is therefore the backbone of of modern grids. And if you want your grids to be smart, in the sense that they would be responsive and flexible uh, and so on, this cannot happen without communication. So in the olden days, or in the classical way of thinking about grids, the load following techniques used basically the physics of the grid and rotating machines to make supply equal to demand. So it is the physics of the grid that actually automatically created a balance between supply and demand, because it was supply that was following the demand on this kind. The physics. So one thing that has happened in the because of the use of storage, and because of the use uh, of renewable generation, like solar in particular, is that rotating machines are now going have less of a role to play. So storage is an electrochemical thing. The solar panels are photovoltaics. They don't have rotating parts. They don't have, uh, don't have the electromagnetic properties of rotating machines. And so consequently, the inertia that you would get from rotating machines is not present, and as a result, we have we are essentially lacking in that aspect. So to substitute for all this, what we need is a digital infrastructure, which can be achieved through communication. So this is basically the smart grid vision, we go away from the from the we use all these renewable sources of energy, but then because they lack some of the physical and mechanical properties that earlier components had, and the grids need, you substitute for that with communication. So without communication, there is no smart grid. Okay, so communication lines have to be established between grid elements to achieve coordination. But then this leads to several questions. So okay, you want demand to change its level. What should you ask it to do? What exactly should you ask it to do? You want it to change from level A to level B? Should you just simply say change from level A to level B, or should you say change to a little? Should you should you do it indirectly in some other way? All of this is unclear. What exactly should you ask it to do? And who should decide the target level? When you ask a demand to change its target level, who actually computes this level? Is this the supply that will compute it? Does there have to be an intermediate entity that will compute it? Who actually decides this? If the supply is directly talking to the demand, in some ways it's okay, because you can say, well, there is now a clean communication channel between supply and demand. But then there is a legal kind of angle that comes up here, because there is a conflict. There could potentially be a conflict of interest letting supply talk directly to demand. So who should decide the target level and who should communicate it is a question in itself. Okay, so this therefore leads this has to be carefully thought through. Now, even if you did whoever sent the command to the demand to change its target level, will the demand respond to your command? What is the guarantee? How do you know that would actually happen? So if they are not going to respond, or if they are going to respond in approximate or in inaccurate ways, how should you compensate for it? Should you exaggerate your requirement or understate the requirement? What should be the approach? Now, what should the demand be offered in exchange for this kind of uh, in exchange for something like this? So, suppose if you did want to change, if you want the demand to change its level, what should the demand be offered? Should it be offered a carrot, a stick, or should it be given no choice at all? No autonomy whatsoever. You just do what we are asking you. And if no autonomy is to be given, how do you compensate them for that no autonomy? Okay. So this is also a question. Now, again, the questions about if you are deciding that you want to use a carrot and stick type of approach, should the carrots and sticks be implicit in some way, or should they be explicit? Should the rewards or incentives that you provide the demand, should they be immediate rewards, or should they be postponed to a later time, or cumulative, whatever? Many different angles are there to this question, and to these questions, they all remain, they all need to be addressed carefully in order to put together this whole concept of a smart grid. Some more questions. So, for example, demand. When I keep talking of demand is actually not monolithic. It is actually comprised of many heterogeneous consumers. Industrial consumers, residential consumers, commercial consumers, etc. So then the question arises that if there is no one entity that you can call demand, should the incentives or carrots and sticks that I was talking about, should these be uniform across all the entities, or should they be heterogeneous? Should the targets that you give to each of these entities, should they be uniform targets, or should they be heterogeneous targets? If they are heterogeneous, what should they be based on? What should they be a function of? Should they be a function of just the consumption that the demand is having, or should they be a function of the history of flexibility that the demand has shown, etc., etc.? There are many questions here. Okay. If you are since you are communicating some amount of some information with the demand, should the same information be shared with each agent of the demand, or should you be sharing in different information? If you are sharing the same information or different information, should that be done publicly or privately? If it is private, if it is to be shared privately, then should it be shared with all or only with a select few? All of these questions arise. So essentially, who are the customers that you should be calling to change their demand level? What is the amount that each of them should change? Whether that amount should be the same or uniform across all customers, or should it be variable across customers? All of this together will help you decide the kind of flexibility that you have. So this has to be put together in a framework of contracts, in a framework of payments, etc., in order to make this possible. So the engineering kind of question that we are effectively now heading towards is a question of social engineering. You want to realize a certain social outcome from the demand or even from the supply side, and for that you need to come up with some interventions to make that happen. Now, but what is the way? What is the framework by which we can think about this? That's basically the question that I will now introduce you to. So when we have physical, mechanical, or electrical type of systems, they respond based on their laws of motion. You give an electrical machine a certain voltage. It will move move at a certain RPM, or move a certain distance based on how it has been based on its laws of motion. The way it has been programmed. here we are not talking of machines anymore. We are talking of individuals, individuals or industries or organizations or shops or something or in the entities like that, which are these entities don't have laws of motion in the traditional sense. So we need frameworks for deciding how exactly are they going to be responding. So the way of thinking about these, the way to think about these frameworks is to is to think of them in what in the framework of economics, which so there is a term that is used in economics which is referred to as Homo economicus. So Homo sapiens are all of us, but Homo economicus are just humans that are Homo sapiens idealized in a certain way, or modeled as economic agents. So it's a term used to describe what we can say is a rational agent. A rational agent is one who acts in his or her interest, given the information that he or she has. To reason through the above questions that I have raised, what we will do is we will assume that all agents are rational. So what this means is that they have a certain interest that can be well defined. There is an information that they have, and what they will do is they will try to maximize their interest. They choose their action to maximize their interest given the information that they receive. So they choose to. So what we will do is we'll use game theory to obtain the outcomes of the interaction of the interactions of such agents. Yeah, and I'll explain more about this in a little while. So now let me come to the question of what is signaling. So a signal is, so now that we know, if our approach is going to be to think of agents as rational agents that have some well-defined interest and some well-defined information, and they're going to respond by maximizing their interest given the information. What we can now ask? Okay, what is the signal? What do I mean by a signal? So a signal comprises of two components. So there's the first component is information. It is the information that you give the agent. And the second is incentive. So an agent's response is a function of two things, as I said. An agent's response is a function of his interest and the information that he has. So you can modify the agent's response by giving him either different information or modifying the way he computes his interest. Okay, or computes his payoff. Okay. So you can either give him an incentive to change his action, or you can give him a different piece of information to change his action. So incentives also come in two different flavors. You can actually give him a direct payment or a penalty for his actions, or there can be indirect incentives. For example, his actions could lead to you can link his actions to the future prices of electricity that he would see in the immediate or in the later future. Okay. So signaling therefore consists of communicating both of these things. So one is the information that you are sending, the other is the incentives that you would be sending. And all of this has to be eventually put in a framework of contract where in the structure of a contract where such and such signals would be sent, and such and such would be the obligations for the agent to respond. Okay, so this therefore comprises of signal. So that's so what I hopefully have been able to do by now is convince you about the need, the need and the importance of signaling in a smart grid, and at least intuitively tell you what comprises of signals for in the smart grid context. Okay. So we'll take a concrete example in a moment, but before I get to that example, I will need to build up a little bit of theory, and that's what I plan to do next. Okay. So let's just make this a little more concrete. So what this means is what we are going to do is we are going to consider each agent or each demand entity to have what is considered what can be called a utility function. So utility function it captures the satisfaction that the agent derives from consumption. So if the agent is a consumer, the utility is a function of the consumption. If the agent is a producer, the utility is a function of the amount that he sells, and so on. A utility is usually an increasing and concave function of the consumption. So you can take, for example, capital U to be log of capital U of x. If x is the amount of consumption, you can take capital U of x to be, say, log of 1 plus x, or 1 minus e to the minus x, or something. You can also put in some parameters here, 1 plus alpha x, e to the minus alpha x, etc., etc. Okay, but usually this is the form that they are concave and increasing. And suppose I ask this consumer to, say, change its consumption by an amount delta x, okay, or reduce its consumption by an amount delta. So then now when he reduces his consumption by delta x, so not only does we can posit that not only does his utility reduce because he's consuming less, but he also has an inconvenience associated with it because because it's a change from normal for. There is in addition to this inconvenience, we can try to model in some way, and then we can say, well, suppose the inconvenience is linear in the amount that you are asking him to change. So if you ask him to change by delta x, then the inconvenience is equal to, say, some inconvenience cost IC of delta x is some I into delta x. Okay, I is some constant. And there is, in addition to this, a usual cost for consumption, or the amount that he has to pay for consumption. So this is, let's say, if he's consuming X, the cost of consumption is P of X. So what therefore a consumer that is who's usually consuming X chooses a reduction delta X in order to maximize this total here. Total here is the satisfaction from consuming x minus delta x, which is the reduced consumption. The satisfaction from consuming the reduced consumption minus the inconvenience that he gets because of the reduction. So IC of delta x there, minus the amount that he has to pay for the reduced consumption, P of x minus delta x. So if his usual consumption level is x, he consume and he is going to be willing to do a delta x to the point where this is maximized. So he will be so if you look at this particular function as a function of delta x, this function the way this sort of function would be, well, that is one where, if your delta is small, then you would be at a certain level. If your delta is too, you would be at a certain level. If your delta is too large, then also you would be at a certain level. There would be an intermediate sweet spot where this function is maximized. The sweet spot delta, which is sort of the optimal level, and that sweet spot will tell you the optimal level of curtailment that the consumer is comfortable with reducing. So an important thing here you would see is that, obviously, if you want to get a reduction here, then you cannot just simply ask him to reduce. He's going to choose his. You can ask him to reduce, but he's going to choose his reduction to maximize this particular. Now, another thing to observe here is that if this cost of consumption is the same as it would be without the reduction, so of course he would be paying less for electricity, but you would also want to maybe, because he's so you would also want to change this price P to make it a little sweeter for him. So the price, uh, the price that he would say with the reduction and without the reduction should potentially be different. In other words, what this is effectively saying is that there should potentially be an incentive also for the consumer to respond. So this is just a very quick example to show you how we approach these sort of problems. Because we don't have equations of motion, and we don't have uh, you know uh, 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 physical laws that govern the entities anymore. We can try to posit economic laws, and the economic law is that we try to think of is that the agent has a utility function, and the agent is going to try and maximize that utility, choose the action that maximizes his net utility function. Okay. Now, obviously the question here arises that how do we estimate things like U and IC and so on? All of these, how do we get all these things? Well, there are many different ways. The past data is usually one way of estimating, because the data tells you how agents have previously performed. So as a result of this, there is an important element in all of these problems of using statistical techniques like machine learning and so on to estimate the behavior of the agent. You can also, of course, perform surveys to understand how what the costs are, to understand what the utility function is, and so on. They also So from the surveys, one gets some idea of how the agents, how the agents are thinking. Now, in either case, one important thing that needs to be done is whatever data you have, whether it's from surveys or it's from some past data, what one must consider is that the data has arisen in response to the prevailing incentives. So you have to make sure that when you are looking at data, be aware that that data is in response to the incentives at that time. It is not necessarily the natural behavior of the or the behavior in the absence of incentives. So what one is getting therefore is the best response of the agent to the incentives that are at play. Okay. So consequently, when you are using techniques from machine learning or whatever to find utility functions for a certain to find utility functions and cost functions from data, the important thing is to make sure you are choosing a model that explicitly accounts for all these for the presence of the incentives. Okay, so for instance, you can what you should try to do is not just fit any sort of neural network or something like that, but rather know that this have some kind of agent-based model in the background, and try to fit this sort of model to the data. Okay, so this is just one high-level thing. Okay, so this is how one agent responds to incentives and information. Now, what happens to when there are multiple agents? And that's the question that I will now take up. Now, what happens when there are multiple agents in the system? If they are all decoupled in some way, that their responses can be independent. Their responses can be independently computed. That's all well and good. Then you can simply use the previous sort of model. The trouble becomes when the responses are actually intertwined. Because, for example, the price in the future of electricity in the future is not just a function of what one consumer does, but what the entire community does, right? So just one consumer curtailing his or her demand is not sufficient, but rather the total curtailment of all consumers is relevant for computing this. So this introduces therefore a coupling between the decisions of the agents, because each agent has to think of what the other agents are also doing during his while choosing his action. So when such coupling occurs, we have to resort to what is called game theory. Okay, so you cannot treat these agents separately. You have to resort to what is called game theory. Now, game theory provides ways of obtaining predictions of interactions of multiple agents when these agents are coupled. Okay, so this is the main sort of tool that we need to put to use when when we are trying to do signaling for smart grids. Okay. So I presume several of you would have may not be aware of the basic tenets of game theory and so on. So what I'm going to do now is take you through some basics of game theory, and then I will tie all of these things together by giving you an example or a case study uh, where we create an agent-based model for curtailment of demand, and using game theory we try to answer questions like, okay, how many agents are to be called for curtailment, how much should you ask them to curtail, and what is the expected curtailment that we can see, and so on. All right, so I'll now take you through a short tour of game theory. So game theory concerns these situations where there are multiple agents, each trying to maximize his or her payoff, but their decisions are interconnected. So the best way to understand this is through a few examples. So here is one famous example. It is what is called the dilemma, prisoner's dilemma. So the prisoner's dilemma comprises of two prisoners, let's say A and B. Now, they are each confined in a solitary room. Okay, so they are each held in solitary confinement in two different cells, and they are both given two choices. The choices are either to testify against the other one, against so they have both been accused, they're suspected of a certain crime, and they have two options. They can each testify against the other person, and or they remain silent. Now, what what the judge tells them is that, suppose if both of you testify, then I will give both of you 2 years in prison. So if A testifies against B and B also ends up testifying against A, they will each get 2 years in prison. If one of them opts to remain silent and the other one testifies, then the one who's testifying will be set free, and the one who remains silent, because now there is evidence against him, he will serve 3 years in prison. So the one who testifies goes free, the one who stays silent gets 3 years in prison. If both of them remain silent, then each of them will get 1 year in prison. So the dilemma for the prisoner is whether should I testify or stay silent. So if you can write out all these numbers, the number of years in prison that they would get in a sort of matrix like I have written here. You have the both prisoners have two choices, either to stay silent or to testify. If both stay silent, then they will both get 1 year in prison. If one fellow stays silent and the other fellow testifies, the one who's staying silent gets 3 years in prison. The one who testifies gets 0. So it's 3, 0. On if the and if the if the row if the one who's choosing testify on the row testifies and the column fellow says silent, then you have the testifying guy gets 0 years in prison, and the column guy gets 3 years in prison, and both testify, they each get 2 years in prison. Okay, so the question we want to ask in a game is what will each player do and what must each player do. Okay, so this is what we are trying to get clarity on. So you can see what's happened here is that these are you cannot reason about these two prisoners independently, because they are what they choose to do depends also on what the other prisoner is doing. And this kind of this leads to this a complication where it's not where you cannot sort of decouple these two players. Okay, so you can think that each player is basically each prisoner or each player here is faced with an optimization problem, and the main thing is that each player has to decide what he will do without the knowledge of the other's decision. And what we want to do as as observers of the game is predict from here what the players would actually do. So here's another game which is called the Hunter's Dilemma. So there are these here. This consists of two hunters. They are they are both poised to either hunt down a deer or a rabbit. They in they both have a deer in their sight, and they are deciding whether to hunt to attack the deer and hunt it or not. Now, if only one of them opts to hunt the deer, he will not be able to hunt it himself. So the deer is big, it needs two people to hunt it. Okay. Now, just as the deer is in their sight, it turns out a rabbit goes by. Okay. Now each hunter has a choice, and the choice is whether to still go for the deer or to go for the rabbit. Now the rabbit is small, and the rabbit can be hunted by one hunter himself. Now, if they both go for the deer, then they will both be able to hunt the deer, and they both get a satisfaction of two each. If one of them goes for the deer and the other one goes for the rabbit, the one who goes for the deer actually is not able to hunt the deer himself, and the one who goes for the rabbit hunts the rabbit himself, and therefore he gets 1 unit of satisfaction. The rabbit is small, he gets 1 unit of satisfaction, and the one who's gone for the deer gets 0. If they both go for the rabbit, then they each get half unit of satisfaction. The question again is what will each of them do, and what must each of them do? Okay. So the important thing here is what will each of them do is a little complicated to predict, because really we don't know what each of them will do. We don't know their personalities and so on and so forth. But we can at least try to put up some set of reasoning rules by which we can predict what must each of them do. Okay, and try to use them to get some sort of a framework for deciding the outcome of such an interaction. So what game theory basically does is sets up a bunch of reasoning rules to help you think through this kind of a situation. Okay, when two or more rational decision makers interact, one would like to have a mathematical framework for reasoning about such situations under certain assumptions. So game theory is the study of such interactions involving strategic decision making. Now, why is this strategic? This is strategic because each player is assumed to be actually acting in his own interest. When the hunter is trying to get the best for himself, each prisoner is also trying to get the best for himself. But what is best for himself cannot be decided until you also consider what the other hunter is doing. So a game comprises of these components. So you have a set of players, let's say 1, 2 up to n. Now for each player you have a set of strategies. Let's call that set Si. And for each player you have an objective function or a payoff function pi i. Okay. Now pi i maps S. S is the Cartesian product of S1 to Sn. So it is the vector of strategies chosen by all players that is being mapped to a real number. So if all players choose each player chooses a strategy for himself, the payoff that each player gets is denoted by pi I of that vector of strategies. Okay. So just to revise, what are the players' strategies and utility functions in the above games? Let's go here. So here the players are these two prisoners A and P. The strategies for both prisoners are to stay silent or to testify. Those are the two strategies for the players. And the payoffs that they will get are clearly a function of both what each of them do. So The first entry here talks of the payoff of the row player, and the second entry here talks of the payoff of the column player. So there are, as a result, uh, there are four possible combinations of the strategies. So four possible strategy vectors, strategy profiles, and for each strategy profile, you have a payoff for each player. So there are eight numbers here in this matrix. In this sort of problem, you have in this problem you have two strategies, either to hunt deer or hunt rabbit for each player, and the players are the two hunters, and the payoffs that you get are as listed in this matrix. Okay, so now what is game theory trying to do? So here's an important thing, that what we are trying to do here is not try to guess human behavior and so on, but rather what we want to do is develop a mathematical or logical framework for reasoning about these interactions. What it attempts to do is simply answer what one can say are the logical outcomes of a certain game. So it thinks of the game as a kind of a puzzle that it wants to logically solve, rather than try to bring in human nature and so on into the picture. So the way game theory does this is that it develops and studies what are called solution concepts. So these are concepts which can be logically regarded as the outcomes of the game, or the outcomes. So game theory provides you with a number of solution concepts using which you can solve the game. And game theory takes the point of view of the observer of the game. It does not take the point of view of a player of the game. So it's very suitable in the case of signaling for smart grids, because what we want to do is what we realize is that there are multiple agents involved, and what we want to do is, as observers or as as administrators of the system, we would want to know what their outcome is going to be. So obviously, as a result of this, it can be used for predicting outcomes, and in many applications, it is known to provide surprisingly good predictions. Okay, what it is not a theory of human behavior, psychology, emotion, trust, etc., or a secret code to win games. That's not what it is attempting to do. It is not trying to do any of that. It is trying to just simply help you logically think through these kind of multi-agent problems. Now, games come in very different flavors. So the first sort of main broad category of games is based on communication requirements. And the communication requirements are between the players. So if the players are allowed any amount of communication between them, and they are known to communicate between them, then the game that results is what is called a cooperative game. So this sort of game, where players can discuss what actions they want to choose they can discuss at length what kind of actions they want to choose between themselves, and can come up even with a binding agreement between themselves to play those actions. A non-cooperative game is one where there is no communication allowed between the players. Okay, and therefore no kind of agreement can be made between the players. So that so if you look at the deer hunt game or the prisoner's dilemma, those are actually non-cooperative games. So when looking at the signaling problems in the smart grid, one of the things one must consider is whether the game that is getting formed, is that a non-cooperative game or a cooperative game. So a cooperative game would be formed when for example, players have a way of collectively choosing their actions. Like, for example, if players are part of a community, or consumers are part of a community in which they know each other and they can collectively decide their outcome. A non-cooperative game is when consumers don't know each other. The consumers are anonymized and have no way to communicate, and so on. Okay. Further classifications that you can make between in games are, you must have heard this term called as a zero-sum game. So a zero-sum game is when the payoffs of the consumers are such that they all sum to zero. So whatever one guy loses, the other guy gains. That sort of a situation is called a zero-sum game. But in many cases, the kind of games we end up dealing with are what are called non-zero-sum games. The other angle is whether there is an aspect of time and the role of information. Okay? Now, if there is no time access, if all decisions are to be made in one shot, then those are what are called static games. If decisions are made sequentially with the knowledge of the decisions of other players, then they are what are called dynamic games. And the quality of information that the players receive, how much do they know about the game, or how much do they know about their state within the game, etc. All of this stuff is what results in other classifications of the game. For example, you have games of imperfect information, you have games of incomplete information, you have games of symmetric and asymmetric information, and so on. Now, game theory is actually closely related to control theory. So many problems in control theory actually come up, can be thought of as problems in game theory, and so on. So game theory covers competitive scenarios as well as cooperative scenarios. A particular type of game is what is called a team. A team is where there are n players that have in which they have a common objective, common or identical objectives. A team problem is one. So many coordination problems or problems with swarms of agents, or or a fleet of generators and so on. All those sort of setups can be thought of as team problems. So in the competitive setting, control theory today also looks at has had to look at problems that involve design of engineering systems like the power grid, and so on, which have an additional aspect of security in addition to the usual considerations like stability, reliability, etc. So game theory therefore provides a natural framework for doing this. In cooperative settings, many decentralized control problems can be thought of as team problems. Multi-agent distributed systems can be thought of as team problems, where each individual components are players. So, how do you apply game theory in general and in this particular context, in the smart grid context? So, game theory you will apply whenever there is a strategic decision involved. So, obviously, in the kind of situation I mentioned for smart grids, strategic decisions are involved about how much to curtail and so on. So, whenever there are multiple agents involved and their payoffs are there, and each agent has a payoff, and their payoffs are affected not just by their own decisions but also of the others. That means there is a coupling between agents. You can apply game theory. Now, there are many different tools and techniques within game theory that you can use, and that needs which one you're using depends on the situation that you're modeling, and that it takes a little bit of knowledge and experience to decide what sort of technique has to be actually applied. Now, the data requirements for game theory are one usually presumes that players know the rules of the game, that they are aware of whatever it is that you are, the way you have modeled the game. Whatever your model assumes is actually, in fact, known to the players. Game theory assumes each player is rational, and so on. And as I said, using the data that we have, we can try to you can try to fit models for the utility functions and so on of the game. So the process flow for applying game theory is to first identify who our players are, identify what kind of strategies they have, identify what their objectives or their payoffs are, and identify the rules by which the game proceeds. So the questions you need to ask are questions like, can agreements on cooperation be enforced or not enforced? If they can be, then it's a cooperative game. If it's not, then it's a non-cooperative game. Can the rules be altered before the game? If so, then this is really actually a case of a pre-game before the actual game in which the rules of the games are decided. Second, are the decisions being taken sequentially or simultaneously? If it's simultaneous, like in the prisoner's dilemma, then what you would end up applying is static game theory. If it's sequential, then you would apply dynamic games. Is there some kind of conflict, or is there sometimes a commonality of interest? If the interests are diametrically opposite, then that results in zero-sum games. If there is some dilemma between cooperation and conflict, then that usually leads to non-zero-sum games. Is the game to be played only once, or is it to be played multiple times? For example, is it what is called a repeated game? Do players have full information or partial information? Okay, that again whether these are, and that also changes whether the game is static or dynamic. Add as much when you're trying to model something as a game, add as much contextual information as possible, and select the appropriate kind of game and analyze it using the tools available in within game theory. So the main tool that I will talk about today is what is called the Nash Equilibrium. So I'm sure many of you have heard of John Nash and probably even seen the movie based on his life. So the Nash Equilibrium is a solution concept that he proposed for solving non-cooperative games. So now when players have no scope for communication or discussion, then you have what is called a non-cooperative game. And therefore, in such a game, there is no mechanism available for letting players get into a kind of binding agreement to play a certain strategy. So consequently, players have to react based on the existing incentives only. Right? So as a result of this, it sort of limits you in the way you can reason about such a game. So so here's some notation for me to define the Nash equilibrium. Suppose if I can write xi as the strategy of a player I, x1 to xn is the strategy profile of the n players. So each player has chosen a strategy. Player I has chosen a strategy xi. Now, if I write x minus I, it just refers to all the strategies of all players except for player I. So it's x1 to xi minus 1, then xi plus 1 till xi. So the strategies of all players except for player I. Okay, and then you have let's say x bar I, x minus I. This stands for this vector where you have x1 till xi minus 1 chosen from x minus I, and in place of xi, I just put x bar I. Okay, so this is the profile that you would get when all other players all other players play x minus I, and player I has changed his strategy to x bar I. So a Nash equilibrium is a profile of strategies x1 star to xn star such that no player has an incentive to unilaterally deviate. That means for every player from 1 to n, you look at the payoff of the play. You look at the cost function of the player, which is that the cost that he would get when all players are sticking to the strategy x star, and you compare that with the cost that he would get if that player alone deviates to a strategy xi, some other strategy xi, while others remain at x minus I star. So the others continue to play the star strategy. This player I changes his strategy to some xi. And it should be that the cost he gets from playing x star is better than the cost that he would get from deviating. So it's in his interest to continue to play x star when xi star when the others are playing x minus I star. And this is true not just for one player I, it is true for every player. So a profile, so x1 star to xn star is a profile of strategies from which no player would want to unilaterally change. Everyone is happy sticking to their own choices, assuming the others are not changing their choices. So it's a profile of strategies XR where if any player I unilaterally shifts from it, he is worse off. Okay. Now it does not take into account the effect of this deviation on the other players' strategies. For example, the other players' strategies are actually held fixed. And the reason you don't take this into account is because the players are not communicating with each other. So there's no, cascading effect that if I do this, then the other fellow would do that. Then that would then make the third person to change, and so on and so forth. This is that none of that is taken into account. If player I changes the strategy, he is assuming the other strategies as fixed. So that's why it is called unilateral deviation. So effectively, what this is saying is that a Nash equilibrium is a point at which once you're dropped there, you would not. No player would want to. It's a stalemate. No player would want to move out of it unless others possibly change. If the others are not changing, I'm not changing. That's what it says. So let's look at, say, for example, prisoner's dilemma. So in prisoner's dilemma, although both prisoners would prefer to actually stay silent because that way they will just get 1 year in jail, it turns out that it is because of the non-cooperative nature of the problem, because they are not able to communicate and coordinate on that particular strategy, they never actually are able to confirm that the other fellow is also being styled. And as a result of that, the Nash equilibrium of this turns out to be is for both players to actually testify. So although staying silent is better for both players in some way, if one fellow is silent, the other fellow always has an incentive to testify, and this makes each of them testify, and then therefore they end up in the Nash equilibrium in which both of them testify. Now, why does this Nash equilibrium make sense in a non-cooperative game? It's because the non-cooperative game has no means for communication. Because communication is not allowed, there is no way for players to discuss and get into an agreement to play a certain strategy. Whatever agreement you think anyone would make, there is always at least one player who has an incentive to deviate from it. And if they are deviating from it, then the agreement breaks and everyone then deviates, and then they all shift to a certain other point. So in the absence of an agreement, is there a question?
No, sir. You said some feedback from you, sir. No.
Okay. Yeah. So since no communication, in the absence of a binding agreement, each player has an incentive to deviate from the silent point. So they would therefore, because knowing that the other fellow is silent, I would always want to testify, because then I have 0 years in jail as opposed to 1 year. And so as a result of that, both players end up testifying. And now Nash equilibrium, there can also be multiple Nash equilibria for a game. For example, the hunter's dilemma, both deer and rabbit turn out to be Nash equilibrium. So now I'll come back to smart grids, and I'll do that through 2 examples. So here's another example of what is of a very important success story of game theory, which is on what is called second price auctions. So so here this auction mechanism has also been used on many auction sites, such as, for example, eBay.com. So the auction here is for a particular there's one object for sale. Okay, there's one particular item like some artifact or a painting or something like that is for sale, and there are L potential buyers, and you have they have a certain value for that particular object. Now these buyers submit bids saying, okay, this is how much I want, how much I'm willing to pay for that particular object. Now, the usual thing would be that usual thing that people try to do is think of is that you would ask if all buyers, you give the object to the one who bids highest, and that's what this auction also does. But you also ask him to pay what the highest bid is. Now it turns out that it was observed that this kind of an auction format actually doesn't give the best possible results because uh, 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 for various reasons it somehow does it's been found that it does not give the best possible result. And so what Vikri actually did was he in fact studied this and showed why this is a problem in what. So the first price auction where a player where everyone just bids the highest possible, everyone bids their price and the highest bidder gets it and pays the highest price. He actually shows that first price auction has a problem, and he proposed a remedy to it, what is called the second price auction. So second price auction is that the highest bidder wins the object, but pays the price of the second highest that the second highest bidder has bid. Okay, so what he pays is the second highest bid. This second price auction changes the nature of the game between the bidders, and it turns out that in this case, uh, uh, it is optimal for players to bid what is their true value. So one of the problems with the first price auction is that players do not end up bidding their true value. They end up
सिंपल सी
underbidding
चीज
or
है,
overbidding.
आप सर ने भी पूछा, आप लोग आपने कंटिन्यूटी इक्वेशन किया है, आपने बोला कि मास कंजर्वेशन.
Uh, so
Yeah, sorry for the interruption. Yeah, you may continue, sir.
Okay. Yeah. So incentives in an auction are complex, and there are often these situations where players end up overbidding or underbidding and so on. And one of the things so what Vikri showed was that you can get rid of all of these problems by having the player bid the second highest bid as opposed to the highest bid. So a bid is so we say that a bid is truthful if a player ends up bidding his true valuation. And it turns out that in the second price auction, truthful bidding dominates all other strategies. That means it's better than playing any other strategy for every player. So since then, the second price auctions have actually become very, very popular. Vikri also got the Nobel Prize for his work and so on. Okay. Now, as I said, this is not the case with the first price auction. So their bidders tend to bid slightly below their valuation. They actually underbid their valuation. So an auction is an example of a mechanism design. So what you're actually doing in an auction is essentially you are creating a game between the players by deciding the rules of the game. So the players are your bidders, and the rules of the game are what kind of how are the rules by which you are going to select the winner of the game of the auction, and how much is he going to be paying for. So this induces a game between the players, and then that game then has outcomes and hopefully the outcomes are what you would want them to be. So mechanism design is essentially the field of creating games between players in such a way that the outcomes are what you want them to be. Okay? So mechanism design concerns designing games so that their Nash equilibria have the desired properties. So this one is so here Vikri basically designed a game between the players with the rule that they should be paying the second highest bid, and that had the property that kind of a game had the property there. Its Nash equilibria has the property that each player is bidding truthfully, and therefore the one who values it most gets the object. But you can consider mechanism design in various ways. Objectives could be to maximize your revenue, could be to maximize a certain social welfare, maximize benefit to consumers. For example, you want to allocate natural resources, induce a certain social behavior, for example, punctuality or truthfulness or whatever. and so on. Okay, so the demand side management in the electricity industry is an important application of mechanism design, and I'll show you an example of it now. But that's not the only application. There are applications in internet advertisements, crowdsourcing, cloud computing, and so on as well. Okay, so so what I will do is I have a few backup slides on a more complicated topic. So what I will do is, before I get to that, I'll just change to a different file and show you some work that I have myself done. So this this is an example of how you do signaling for demand response. Okay, so this is joint work with Professor Anupama, who you heard yesterday. So this is the problem we are talking about here is addressing the problem of free riding in voluntary demand response, and I'll show you how we'll use game theory to address this problem. So once again, let's recall the background. There's uncertainty has always existed on the demand side of electricity. Traditionally, supply has followed demand, but renewables have contributed to supply uncertainty on the supply side also. So, and demand response involves modification of consumption of users in response to changes in supply. And what this hopes to do is to close the loop from supply to demand to iron out any potential deviations from scheduled operations. So as I said, there are for demand response there are multiple challenges. So first, the main challenge is how do you retain the autonomy of consumers? Why would they, consumers are, if they're autonomous, why should they alter their consumption? So therefore, there are two approaches taken. Which first is direct load control, in which you give no autonomy to the consumers. A consumer simply signs a contract that gives the utility direct load control, direct control over his load. Another is to have price or incentives that are so that users are incentivized by the utility, either through price signals or through explicit payments to modify their consumption. There are challenges in both cases. Challenges in the direct load control is that consumers are not readily willing to give up access to their loads. There are also concerns about privacy, profiling, and so on. And there are also challenges about the incentives. When you are giving incentives, that is a challenge as well, because at the end of the day, the business of the utility is to sell electricity. It is not to give people incentives to reduce electricity. Incentives cost money, and also result in less electricity sold. So the other main challenge is the lack of observability of the states of the consumers. You do not know if how many consumers are going to actually respond when you provide them a certain incentive. So the basic design question for incentives are as follows. So we are mainly concerned about load curtailment. Okay, so there is a lack of observability, means that utility does not actually know what the consumer's willingness or availability for demand responses. So utility does not know which consumers are available for providing demand response services. So consequently, what it ends up doing is calls more consumers than required for achieving the desired level of curtailment. Okay, so if it needs 100 consumers, it might call 110 or 120 or whatever. It calls more consumers than are required. Now, what this creates is a problem of free riding, because there are more consumers than needed. Each consumer can think that the other one will do the curtailment, and I will ride on his curtailment. So there is an inconvenience associated with curtailment, and consumers may prefer not to curtail and rather free ride on the curtailments of others. So on the other hand, if you make the incentives too attractive, too many consumers will respond, and then that creates that's a separate problem altogether. So question becomes therefore, how does one address the free rider problem? What is the optimal level of incentives? How many consumers to call? How many customers to call for providing these DR services? So here is going to be our approach towards this. So when a DR event happens, we say a DR event happens when there is a need for some kind of curtailment from the consumers. The utility calls upon a set of consumers. So there is a communication channel between the utility and the consumers. The utility calls upon that set of consumers to curtail their load from the larger pre-contracted, from a larger pre-contracted pool. So there is a pool of consumers that has already entered into this contract, which tells the which gives the utility the right to call them to to curtail. But whether they will actually curtail or not is still the choice between with the consumer. Okay, it just gives the utility the right to call them. Okay, so so suppose n consumers are called to curtail a fixed amount. Each of them is called to curtail a fixed amount D. Okay. Now, when called, consumer I can find himself in two possible states. Okay, let's say his state is Ti in a set capital Di, and it is privately known only to the consumer. It is not known to the utility. Now, and this vector T1 to Tn is realized with a probability P of T. And the probability of that, although the state of each consumer is not known, this probability distribution is known to all. The curtailment itself is voluntary, because after being called, the consumer may still choose to not curtail. But if the consumer curtails, he will get an incentive for it and face an inconvenience, regardless of whether a DR is successful or not. But if he does not curtail, there are two possibilities. If enough curtailment is obtained from everyone, there is going to be no inconvenience for the consumer and no penalty for it. But if enough curtailment is not obtained from everyone, then he has to pay a penalty. Okay, so if he curtails, no problem. He gets he faces an inconvenience, but is guaranteed electricity supply and is also given an incentive. But if he does not curtail, then there are two possibilities. If enough other people curtail, then no problem, he gets away. But if enough other people do not curtail, then he is going to be penalized. So in other words, all those who did not curtail get penalized if enough curtailment is not obtained. All right. So this is the model. Now, what we'll say, what we'll assume is that the consumers are in two possible states. One is that they can curtail and they cannot curtail. That is denoted by C and N. Curtail or not curtail. Okay, they can curtail or cannot curtail, and they make a binary choice, which is the choice itself is whether to curtail or not to curtail. So these are the actions that the consumers can choose. So that now, if the consumer is in a position to curtail, he has the choice. He can say either yes or no. He can either curtail or not curtail. If he is not in a position to curtail, then he has no choice. He's always going to say no. Okay, and we will say that DR is sufficient if capital K consumers curtail. That means if capital K consumers take action Y. Okay? Now, when a consumer takes action, when a consumer I takes action Xi and others take action Xj, all right, the payoff that the consumer I gets is this. So is given by this particular expression. Now this expression looks a little complicated, but it's very simple actually. You have the consumer faces a certain cost of taking that action. That's C of xi. Now if he says yes, he's going to get u upper bar, and that's the benefit from that's the benefit that he would get from when there is sufficient D. That's essentially the benefit that he would get from sufficient DR. Okay. If he takes the action no, then there are two, as I said, there are two possible cases. If enough of the other guys curtail, so this hash of x minus I is the number of other consumers taking action y. So if enough of the other guys curtail, then he gets u upper bar. If enough of the other guy, if there aren't enough other guys curtailing, then he gets an action u lower bar. This is his utility described as this is the payoff that he has as described above. Okay, so complying consumers, in other words, always draw benefit u upper bar, no matter whether there is enough curtailment or not. Because those who comply with the utility get the benefit they draw is u upper bar. If they do not comply, okay, the benefit they get is u under bar. Now u under bar is less than u upper bar, and that is in the case if your demand response is insufficient. So the differential benefit, that is u upper bar minus u, can be achieved via either a penalty or an increase in tariff. Right. So either on the non-compliant consumers, if your demand response is insufficient, so you can think of the difference u upper bar minus u lower bar as the penalty that is being charged to the consumer. Now the cost function of taking an action is the cost of inconvenience, the electricity charges for the reduced load, minus any incentive that is offered by the utility that the utility has to offer. All of this put together gives you the cost. Okay, so cost of saying no is just simply the electricity charges at the usual load. So if you take Cy minus Cn, this is inconvenience minus savings minus the incentive. And we are going to assume that cost of saying yes is greater than the cost of saying no. So the incentive is not large enough that it overshadows the inconvenience cost. Okay. So we'll also assume consumers are prone to free riding. Now, what does this mean? It means if you look at these three payoffs, first is U bar minus Cn. This is usual load at usual prices. That is most preferred. Then usual load from curtailment, that is next. And then the next is no curtailment, and if your DR is unsuccessful, that is the least preferred. That's the least preferred situation. Okay, so now what is the strategy of a consumer? In this case, the consumer is going to the action that the consumer has to take is a function of the state that he finds himself in. The strategy has to be also chosen as a function of the state. It's not just one action, but actually a function of the state. So he has these two possible functions. The first one is curtail when you can, what I call CWC, and the other is never curtail. So curtail when you can just simply says that whenever it's possible, you will curtail. So that's his policy. Whenever I'm called, I will curtail. The other is to say, well, doesn't matter if I'm doesn't matter whether I'm called on. Doesn't matter if I'm called, if I'm available or not available. Whenever I'm called, I'm not going to curtail. So that's your never curtail policy. Okay, and you can write out the payoff that the consumer has as a function of his state, the expected payoff that the consumer will get, which is called his Bayesian payoff, as a function of his own state under each of these policies, assuming the other players play their own policies. Right. Now, what you can do is you can do for something more. You can actually randomize over the choices of these policies. It's what this gives you what is called a mixed strategy. And so that basically says curtail when you can with a certain probability and never curtail with a certain other probability. You can, through this you can write out an expected payoff of that the consumer would have when he is in each of the states, when he can curtail and when he cannot curtail. And then you can now look for a Nash equilibrium in this randomized space. Okay, so that's what is called a Bayesian Nash equilibrium. Why one start? So it's a probability of playing one of these, each of these strategies. So here's a here. So after you do this analysis, it turns out you can do a few calculations. You can and show that, well, it turns out that there is a certain you can actually show that there is always a Nash equilibrium to this game. You can compute how many, what, when, what is the fraction of players playing each of these strategies. You can characterize the equilibrium of this game and what sort of strategy, what kind of players use what kind of strategies, and here's the main result, which is that you can compute the expected curtailment from this. So if each player is going to randomly decide to play this or that, but that random choice is also strategic, you can, from this you can decide, you can get what the mean curtailment that you would expect is, and what the variance of this curtailment is. Because the curtailment itself is a stochastic thing, because given that players are going to be in various states and their actions are also going to be variable, every now sometimes they're going to randomize over their actions also, you get a certain expected curtailment and the variance of this curtailment. So you can now you can try to plot some of these terms. So what I have here is delta. Delta is here captures the incentive that is being offered. So lower values of delta means higher incentive. Larger values of delta means lower incentive. So as you see that as you increase delta means you reduce your incentive. On the y-axis I have the curtailment that is induced. So as you increase your incentive, the curtailment as you decrease your incentive, the curtailment actually reduces and then goes through a steep fall. Eventually comes down to you get almost no curtailment. If your incentive is too good, then suddenly you also get a certain steep increase where suddenly pretty much everyone begins to all players begin to curtail. So the optimal incentive that you want is somewhere in between. The right incentive level can be eyeballed by looking at how many how much is the curtailment that you want. Like suppose if you want 10 units of 10 people to curtail, then what is the incentive that you need to have? And if you want 15 people to curtail, what is the incentive you should have? The bars on this tell you the variance that you have. So the how much that tells you what the variance the variance is going to be of that around that particular point. How many consumers to call also is something that we can decide by looking at the looking at from there. So what by changing the amount of incentives, you can you get so then so the if you need 10 people to be 10 people to respond, how many should you be calling? You should be calling 20, 30, 40, 50, etc. So you can plot these kind of curves also, then as a function of the incentive. So for each of them, you can say, well, if you need a curtailment of 10, the curtailment that you would actually get when you call 40 people is given by this orange curve as a function of the incentive. So you can now eyeball what based on how much incentive you should be having and how many people you should be calling in order to get a certain curtailment. Right. So this is an example of doing signaling. So what we have done is we have sent signals to which involve some incentives and some information. We have told players that we need a certain amount of curtailment. We have told players that only a certain fraction of them have been called. We have told them that this is going to be the situation, that if they if the DR is unsuccessful, then they'll have a penalty. If not, they will have if it's successful, they should be okay. If they curtail, there should be no problem, etc., etc. All of this has been signaled to the players. And now the model actually tells you how they are going to be responding. So you can actually use a model like this with, by fitting in your utility function, the utility and so on to the data. You can actually use a model like this to predict what's going to be the response of the customer. So what I've just shown you is a voluntary systematic framework for voluntary demand response. One of the main things we find in this thing is actually that incentives are more important than the pool size. The sensitivity to incentives is a lot. If your incentives is too small, there's a huge dead band actually in which incentives have no bearing. But if your incentives go outside that band, they become either too low or they become too large. If they're too low, nobody participates. If they're too large, everybody participates. They have to be carefully tuned. Okay, so this is what I had planned to present as an example of signaling for demand response. I have more complex material also, so Matthew, we've done with 1.5 hours. So what would you want to do? Should we continue or would we?
Yeah, I think this much itself is enough for the day.
Okay.
Yeah. So if anyone is further interested, they can read the paper. I think it's already published in Indian Control Conference.
Correct.
Right? Yes.
Correct.
So maybe we will share the video as well. So the content is enough because they need some time to digest these concepts. So
so that audience has, I can take questions if they want to ask anything.
Yeah, the session was fruitful and a fantabulous one. Now it's query time. If anyone have any doubts regarding the topic, you can directly ask the questions to respected Dr. Ankur.
Yeah, if anyone has any questions, they can unmute themselves and ask, or else you can directly mail to Ankur as well. The mail ID is there in his personal website as well.
Yeah. So feel free to reach out to me if you have any questions, or if you want to just send your questions to Matthew, and Matthew can send them to me. That is also okay. Or through if there's a way for you to get it through the feedback form or something.
Yeah. Thank you, Doctor. Thank you for enlightening us with such bright thoughts on smart signaling frameworks for smart grids. Thank you.
Okay. Wonderful. Thank you so much. So Matthew, should I log off then?
Yeah. Thank you, sir. Thank you.
Okay. All right. Okay. Thanks a lot.
Thank you. So the next session, we'll have the next session at 2:30 in the afternoon. So the same link you can use to log into that session. So that will be the power electronic solutions integration of renewable into smart grid. So we will meet on that session at 2:30 in the afternoon. Okay. Thank you very much for joining. Thank you.
Okay. All the best for the rest of the FDT.
Thank you, sir.